Welcome everyone. Today we are diving into how quantum computers actually work, a topic that blends physics, math, and computer science into something that could reshape the world. Traditional computers use bits, zeros, and ones to process information. Quantum computers use qubits, which obey quantum mechanical laws. These allow them to explore vast computational possibilities simultaneously. That's what gives them such immense potential for speed and power. A qubit isn't limited to just a 0 or 1, it can be both at once, thanks to superposition. Think of it like spinning a coin until it lands, it's not just heads or tails, it's both. This means a single qubit holds far more information than a classical bit. We use the Bloch sphere to represent all the possible states a qubit can be in. This makes quantum computation incredibly rich in parallelism. Next, we have entanglement, often described as spooky action at a distance. When two qubits are entangled, the state of one instantly determines the state of the other, no matter how far apart they are. This is critical for quantum computing. It enables interactions and computations that are impossibly classical, such as quantum teleportation or massively parallel information processing. To build quantum algorithms, we use quantum gates, the quantum equivalent of logical operations. Gates like CNOT and polygates manipulate qubit states, often entangling or superposing them. Quantum circuits are built by arranging these gates in sequences. Unlike classical circuits, these are reversible and based on unitary transformations, which means they don't lose information. Once we are ready to extract answer, we measure the qubits. These causes their wave functions to collapse into classical states 0 or 1. Before measurements, they hold complex quantum information. After measurement, the richness is lost. Measurement is irreversible and probabilistic. So, we often run quantum computations multiple times to get statistically meaningful results. So, why do we care this? Because of the quantum speed up, quantum computers can evaluate multiple solutions simultaneously. Shor's algorithm, for example, factors large integers exponentially faster than any classical algorithm, posing a threat to modern encryption. Grover's algorithm speeds up search tasks. Quantum parallelism allows us to explore solution spaces in fundamentally new ways, changing the game in optimization, cryptography, and beyond. However, qubits are fragile. Decoherence occurs when quantum information is lost to the environment, ruining computations. To fight this, we use quantum error correction. Instead of one physical qubit, we encode information across multiple qubits to detect and correct errors without destroying the quantum state. This is essential for building reliable quantum systems. There are several hardware platforms for quantum computers. Superconducting qubits like those used by IBM and Google use tiny circuits cooled to near absolute zero. Trapped ions are ultra-stable, manipulated with lasers. Photonic systems, which use particles of light, are promising for communications and potentially more scalable systems. Each technology has trade-offs in speed, coherence, and scalability. Quantum algorithms are where all this power gets put to use. Beyond Shor and Grover, we have algorithms for quantum simulation, modeling molecules and materials at an atomic level. These are already being tested in drug discovery, battery chemistry, and material science, and we are scratching the surface of what's possible. In conclusion, Quantum computing holds revolutionary promise, but we are still in early stages. Building large scale, fault tolerant quantum machines is a major challenge, but one we are rapidly addressing. In the meantime, hybrid systems, classical machines assisted by quantum processors, will bridge this gap. And as quantum power grows, so does the need for quantum safe encryption, global governance, and ethical foresight. Quantum computing isn't just the future, it's actively being built now. Thank you.